Hello, this is Aarti Kulkarni and today I will be presenting a topic of traffic sign classification using convolutional neural networks. Before jumping into what the problem statement is, the choice of topic was because traffic sign classification and detection forms an important part of the road infrastructure system, as traffic signs are heavily used to guide the drivers and the flow of the traffic. Traffic signs give drivers a clear idea of the upcoming road conditions and are thereby used to reduce the number of accidents caused while driving. Traffic signs also come with drastic environmental conditions including fading light, blurriness, haziness, unclarity of the traffic signs that are present on the road, and hence this system of traffic sign detection and classification was first introduced. Traffic sign detection and classification is not just a convolutional neural network system that can be solved at any point of time, but it requires results to be delivered in a real-time environment conditions. By real-time environment conditions, it means that the time required to detect and classify the sign has to be small, because then that is how the traffic signs can be recognized by the driver and the implementation of the change in road conditions can happen. There is a high requirement of perfect accuracy for this, because anything that goes wrong with the identification of the traffic sign may cause accidents, and any increased time in detection and classification of the traffic sign will also do the same. Traffic sign detection and classification systems have been developed for a long time now, but the ones that have been developed as of now using deep learning based convolutional neural networks are the ones that are owing to the reduced usage of computational resources. Jumping into the prior work, before convolutional neural networks was used for traffic sign detection and classification, computer vision based techniques were used. Although these techniques worked completely fine for detection and classification, they were unable to overcome the problems of the noise in the image data set, or the fading lighting in the image data set, or the haziness. And this was an important aspect to be overcome, because this is what the real-time condition of traffic signs on the road looks like. These limitations were including the detection and classification that was based on the shape and color of the traffic sign only. This was creating problems because the shape and the color of the traffic sign also depend on the lighting that is available on the traffic sign on the road. In case of change in lighting or illumination, it can cause an incorrect identification of the traffic sign when the algorithm for detecting and classifying the traffic sign is only dependent on color or shape. The shape of the traffic sign can be lost in haphazard way of the traffic sign due to unprecedented conditions. Another of the prior work that was done for this problem was where two CNN networks were used, one for detection of the traffic sign and another for the classification of the traffic sign. Although this works fine, this requires a very high computational resources, which not always might be available. So classification of neural using convolutional neural networks. And convolutional neural network is basically a deep learning based approach that is used to classify image data set. So for convolutional neural network works in such a way that an image in data set is given as input to the network, and then the network processes this input via its multiple layers. During this process, The important features of that image that are relevant to the output classes are picked by the convolutional neural network, and an importance is assigned to all of these features of relevance that are picked from the images, and then the images are classified into the number of output classes present. So convolutional neural network basically consists of these distinct layers, including convolution layer, ReLU layer, which is an activation layer, pooling, and flattening, which converts a 3D output to a 1D output in a fully connected layer, and a softmax layer, which finally converts the output into the form of the output classes. The data set used for this problem was the German traffic sign recognition benchmark. This data set is a widely used data set for this kind of problem because it consists of various number of images of the traffic signs that are not local but globally recognized, so it creates a wider application of the problem. This dataset consists of single images of traffic signs which are identified by their respective class IDs. The class IDs are stored in a CSV file. The images are a total of divided into a total of 43 classes and are over 50,000 images in a single dataset. This dataset consists of all types of images, including triangular signs, circular signs, speed limits, basic signs of stop and no entry, etc. So before jumping into the training of the network, every data set has to be pre-processed. The reason behind using CNN as an approach is that the level of data pre-processing is reduced comparatively to the techniques that were used before, but certain techniques of data pre-processing have to be used. These techniques include reshuffling, grayscaling, local histogram equalization, and normalization. Reshuffling of any data set before being used is important to increase the randomness of the model, which increases the stability of the model. If reshuffling helps every data point in the input data set have an independent and unbiased effect on the model. Grayscaling is used so that the image can be converted into from a 3-layer image to a 1-layer image, thereby reducing its complexity. Grayscaling also helps in removing the noise in the data set. Local histogram equalization is basically used because in this case the images are real time and are subjected to change in light and varying illumination. So to overcome the problem of low contrast in the images, local histogram equalization is used. Normalization is used to basically convert the range of pixel intensity values. So normalized data is converted into a scale of 0 to 1, and it has an effect on the low noise, and the high frequency noise can be overcome with this. Normalized data set is reduced down to 0 mean and equal variance. So the two networks that I have experimented with to find out the network that gives the best accuracy are LINET 5 and VGGNet. This particular network is a convolutional neural network architecture that consists of 7 layers in total. These layers comprise of the convolution layer, subsampling layer, and the fully connected layer. This network was initially developed for recognizing handwritten digits, and it can be reused for the traffic sign classification and detection problem because initially the data set on which this network was trained also reduces every image down to pixel values, which can be used for the traffic sign classification problem as well. The other network is the VGGNet, which is a convolutional neural network that consists of 16 to 19 layers in total. These layers consist of the convolution layer, the ReLU layer, which is an activation layer, pooling layer, and the fully connected layer. VGGNet is an architecture that was developed so that the focus from the hyperparameters could be reduced and could be instead put on the convolution layers itself. Hence VGGNet was designed as a network that will have less number of layers with more focus on convolution layers itself instead of it being dependent on hyperparameters. The performance evaluation of running for both the networks gave an accuracy of 93.039% for the Linet 5 and 98.821 for the VGG net. And both of these accuracies were developed on the validation test set. The test accuracy turned out to be 96.9%. The image that shows a confusion matrix, and the blocks that are present in the confusion matrix show that although a lot of the classes are identified as true classes, there are some of the classes that include signs like a yield, triangular signs, or even speed limits. Those are not identified to the best accuracy possible. Speed limit signs are identified as speed limits, but the speed limit written in the image can be misclassified to a certain extent. The future work that can be done to improve on the accuracy that is already achieved is that the data set could initially be divided amongst classes, and then the network could be trained separately on the classes itself. This will improve the performance of the network on certain classes on which the accuracy is not turning out completely well, like the one that I mentioned before, where the speed limit sign is recognized as a speed limit, but the limit that is present inside of the sign can be misclassified. This problem can be overcome by dividing the input images into classes and training the network on each class itself. So, in conclusion, deep learning based convolutional neural networks can help overcome the problems in the data set of noise and lighting and blurred images, etc. CNNs also help achieve higher accuracy and less detection times. The CNN are used instead of the computer vision techniques used before, so that real-time results can be achieved, which is very important in a road infrastructure system. Thank you. This is the presentation.